Hi, so this video is a request from Anastasia, and she in the comments wrote this. Theoretically, you cannot count 1, 2, 3, and so on a traditional number line because between each real number is an infinite number of decimal places that fill the space between each number. If we applied the same principles of pi to this, it would be possible. So thinking about it like this, how would this apply to general mathematics, and would this be something worth teaching to a class? Also, has anyone ever hypothesized this before, or tried to apply it to any other form of math, such as calculus, algebra, finite math, and so on? So that's a great question, and I'll address a little bit of it. This kind of reminds me of Zeno's paradoxes. And Zeno had several paradoxes where if you think of something one way, it's impossible, and the other way, it's very obvious that it would work. So one of these is if you dropped an object, so if I drop this pen, it hits the desk there. But if you think about it the way that first it has to fall halfway and then halfway again, then halfway again and halfway again, it would actually then never reach the desk. So how come when you think of it one way, it works and the other way it doesn't? Another one of these is Achilles and the tortoise. The way that works is that if the tortoise gets a head start, then if you think of it one way, Achilles can never actually pass the tortoise. So there's a paradox there. But this one actually reminds me a little bit about the arrow. And if I remember that one correctly, it's the idea that any motion would be impossible. And so if you're taking an arrow and you're shooting it from here and it's going to hit over here, then what happens is that it just doesn't appear from the beginning to the end. So it has to reach someplace in the middle first. But when you start off the arrow, it just doesn't appear at the middle place. It has to first reach a place in the middle of that. And so if you take any 2 points, the arrow just doesn't appear from one point to the other. It has to go to the points in between, and therefore the arrow should never move. But when you shoot the arrow, it obviously goes the distance. So what's the paradox there? And that's what this comment reminded me of, because it's like, well, how can you count to 1, 2, 3, where if you have to take all those little steps in between, you actually wouldn't get anywhere. And this really has to do with this idea of zeros and infinities. And so what's happening is that the reason you can move forward is because, yes, there's an infinite amount of points in between, but they're getting smaller and smaller and smaller. And so what's happening is that those points get closer and closer to zero, but you have an infinite amount of them. So you have this infinite amount, but they're infinitely small. And so when you have 0 times infinity, who wins? Anything times 0 is 0, but when you have infinity, that's infinitely big. And so this is what's actually called an indeterminate form. And there's actually 7 different indeterminate forms. And you could study about this in a calculus class, for example. If you look up indeterminate forms, when you have something like 0 times infinity or infinity divided by infinity, it really depends on the context that you're in about what it actually would be equal to. So 0 times infinity could be pi, or it could be 7, or 9, or -2. It just depends on the context of that. So that's really what that question has to deal with. And maybe I'll make another video about all the wonderful things with infinity. There's some other really cool things. But here's just one quick demonstration I'd like to share with you that kind of reminds me of what it is that you're talking about. Let's say we have this long line here and this short line. And if I said which of these lines had more points in it, by looking at this, you would say, well, the longer line has more points than the short line. However, they actually have the exact same amount of points. And here's one way to demonstrate that. If we take the small line and make it into a circle, so it's the same length, it has the same amount of points, we've just curved it instead of having it straight. And we'll do the same thing for this longer line, and we'll make them concentric, so they both have the same center. So if we take any point from the larger circle and we connect it to the center, it has to go through the smaller circle. So this point here on the large circle corresponds with this point here on the smaller circle. And if I make another line from the large circle to the center, this point on the large circle corresponds with this point on the small circle. And I can keep doing this forever, where every point on the large circle will match with exactly one point on the small circle. And since we have every point matching, they have to have the same amount of points. You can't find any extra point on the outside circle that doesn't have a match on the inner circle. So that's kind of another way to think about, what does infinity really mean? And so I think these are great questions. And I don't know how old your son is, but it's great that he's asking those things. These are questions that people have asked for thousands of years. And the exploration of that first started off as philosophy, but then it eventually turned into a more deeper understanding, which became mathematics. So in a way, a lot of mathematics was built to try to answer these types of questions. So I think it's great that that's what you're exploring, and I hope this video just helped to answer that a little bit and give you a little inspiration. But I would definitely talk about these kinds of things with your students. Thank you.